All right, welcome back, everyone. So of course, earlier in the book, in particular in chapter 1, we talked about another type of transformation known as the rotation matrix or transformation of coordinates. So of course, there's going to be parallels between the rotation matrix and the Lorentz transformation. And this is even more striking if we introduce the concept of rapidity, which is defined as theta equal tan hyperbolic tangent, of course inverse, of V over C. All right, so our goal here is to express the Lorentz transformation matrix, lambda, in terms of theta and compare it to the rotation matrix that we saw back in chapter 1. And then part B, express the Einstein velocity addition law in terms of rapidity. So we got a couple cool things to deal with, and let's see how it all plays together. So again, the Lorentz transformation matrix alone, again in the x direction here, was given as lambda equal this. Y and z don't transform because there's no length contraction or time dilation to deal with. Everything is traveling in the x direction. So the zeroth component, zeroth row, zeroth column, that has to do with the time element. Everything else here, these 9 components are all spatial defined. So that being said, if we see that theta is equal to the inverse of the hyperbolic tangent, then we know that tangent is equal to V over C. But we let beta equal V over C for everything else, so we're saying that beta is equal to tangent. That being said, now let's define gamma in terms of this hyperbolic tangent. So square everything, and then of course 1 minus tangent squared in the hyperbolic sense gives us the secant squared, the hyperbolic secant squared. And then of course we have a square there and a square root, they undo each other. And now we see that we're left with a 1 over the hyperbolic secant, which gives us the hyperbolic cosine. Well, that's a pretty cool result, quite frankly. And then of course we multiply the gamma and the beta. We know that hyperbolic cosine times hyperbolic tangent gives us the hyperbolic sine. Who would have thought? That being said, this can't be just coincident. This actually joins together nicely. How nicely? Well, if we see that we just put in the definitions for the gamma and the gamma beta, and then gamma, gamma beta, you see that based on where we're actually trying to transform, these three, of course, we just write that as an I for this diagonal term. So if we put that to an I, it would be even better. But you see nonetheless that there is a very big parallel here. Hyperbolic, 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 minus sines and sines, boom, boom. So there actually is a very quick comparison to it, and it's actually really cool to see that. And again, we'll have an exploration of this later on in the chapter. So moving on to part B, if we wanted to rewrite the Einstein velocity addition law with the definition for tangent, let's go ahead and be careful and start doing the best we can. Here, algebraically, we know what we need to from the Einstein rule, but what we need to do is write everything in terms of 1 over c's, so we can put the proper beta terms in there if we needed to. That being said, we multiply by 1 over c on both sides, so we get a 1 over c here, and in the numerator we just distributed in. So that's where the c's came from. And of course, in the denominator we split them up independently. That being said, the hyperbolic tangent of whenever we're rotating, so that would be phi bar, is cosine or tangent phi hyperbolic tangent theta, and in the denominator repeat. But this fraction is actually a hyperbolic trigonometric identity for the sum and difference formula. So what this is, if you go back to the tangent sum and difference formulas from regular trig, put it in a hyperbolic perspective, or use the exponentials if you wanted to, you would see that this is hyperbolic tangent of phi minus theta, which is equal to the transformation of phi bar, or phi bar is just equal to phi minus theta. So that's actually really cool to think about. Same thing that we thought about in the chapter 9 when we dealt with the exponentials for the complex wave function. Turned out that all we dealt with was the plus or minus of the arguments of those exponentials, instead of having to combine trig functions. So once again, the perspective that we can take on some of these is really fascinating, but it's not always obvious until you dig into these. So props to the author for making this a question to deal with. It always fascinates me how they find out what needs to go where. That being said, expect this to pop up later.